Hello, everybody. I'm going to present you results on product prediction for copper-tube straightening machine using neural networks, a joint work with my student Ioannis Kalatzis. Well, the objective of this study is the development and implementation of an artificial neural network applied to dedicated machine designed for straightening coiled copper tubes. The ultimate goal is to predict the effects of machine setting adjustments on the characteristics of the final product. The overview of the design and construction refers to a diameter 12 millimeters copper tube straightening machine. Literature review and the theoretical background on artificial neural networks resulted to our methodology that is used based on experimental procedure and data collection. The implementation follows on an artificial neural network realized in MATLAB. Conclusions and implementation hints finish this presentation. This is the overall setting of the machine and the primary alignment mechanisms. These are the photos of the machine that has been constructed for a client of the company of Mr. Kalatzis. This is the setting here together with the copper wire passing through this machine. And on the other side, you see the straightened bars cut it at specified lengths. This is the final machine constructed, and these are the partial components of the machine from the rotary decoiling turntable, initial guide B here, initial guide rollers, horizontal forming rolls, vertical forming rolls, copper tube rollers, and circular saw for cutting the straightened sections and the collection of the product at this part. Well, the state of the art, literature review was conducted regarding the application of neural networks, but no relevant research was identified. The core concept of neural network is to establish correlation between data that do not inherently conform to predetermined mathematical models, emulating the way the human mind processes information through observation. These are the different variables that can be adjusted. For example, horizontal rollers are adjusted to random position at the beginning, measurement of horizontal roller position using the depth goes, and subsequent loading of the data follows. Extraction and disposal of a copper tube segment equal in length to the entire roll-forming assembly follows. Cutting of a 1 meter sample follows. The sample number is also recorded to correlate it with respective machine setting data, and the aforementioned steps are repeated from the beginning until a total of 10 samples are produced regarding the horizontal roller configurations, and then the vertical roller configurations follow. Where the measurements are taken by follow this methodology. Here are pictures documenting the measurement of the various parts. You see here the part that has an obvious curvature. Well, the data has been collected and presented in various plots like this one, x-axis curvature for the fixed vertical rollers, for the fixed horizontal rollers, and so on. Y-axis curvature, again, for fixed vertical and fixed horizontal rollers. Then the data are prepared for usage within an artificial neural network, feed-forward backpropagation neural network. Several steps, two-phase methodology, by putting the horizontal roller data with the x-axis, by putting the vertical roller data with the y-axis, and for each phase, the results of the interaction yielding the optimal approximation out of the 10 algorithmic executions are selected and presented. This is the neural network for the x-axis. These are the results documented and compared with the accurate ones. This is the training state. This is the y-axis, again, documentation of training, and the performance evaluation. The error histogram and the performance plot shows the advantages and disadvantages of this application. Well, in the x-axis, the summary is as follows. The training fit is exceptional with the R-value approximating unity. The validation fit is highly satisfactory. The test fit is optimal with a moderate R-value. Regarding the model's generalization capability, it is not highly robust, as clear indications of overfitting are observed. The same procedure has been followed for the y-axis performance evaluation. The results are again the following. The training fit is exceptional, the validation fit is strong, and although the testing dataset exhibits an exceptionally high correlation coefficient, the corresponding fit line demonstrates a biased slope deviating from the ideal unit trajectory. Regarding the model generalization capability, it can be characterized as moderate, given that both the validation and testing errors are noticeably higher than the training error. Well, the overall results and the overall evaluation indicates that the model has not reached an optimal performance level. Potential factors contributing to this outcome are insufficient input data set size, omission of additional input data which might play a role in the final configuration of the products, such as the pre-bending already present in the copper tube, as it originates from a coil form during each sample collection, temperature variations, etc. The exact wall thickness of the copper tube at each point, which might not be constant due to its manufacturing process. Some optimization proposals and recommendation for the future. It would be possible to utilize more advanced artificial neural networks. In order to incorporate temporal correlation into the model, input vectors must be structured to include historical data, whereas to establish spatial correlation, inputs must incorporate values from adjacent nodes. Consequently, retraining could be performed by utilizing tools such as PyTorch, Geometric, and Deep Graph library, which are specialized Python-based libraries. And finally, finite element modeling could be used in order to produce additional training data, a kind of fusion of experimental and numerical data that could enhance the performance of the proposed scheme. Thank you very much for your attention.